So yesterday, finally started with log Gromov-Witten theory, and you saw some of this already in action in Pierrick's talk. So let me just remind you quickly, very quickly, what there was. So we had this notion of basic stable log maps. So first, stable log maps was just a map from enrichment of usual stable maps with log geometry. They come with a type that has to do with the tropicalizations, a kind of discrete data coming defined by a tropicalization. And very important is this data of contact orders. So that's additional input data that you keep fixed in your problems, additional input data to Gromov-Witten theory. And then I did a few examples, and we had the moduli spaces, and then I try to convince you that these moduli spaces in log Gromov-Witten theory come with an interesting map to a slightly modified base. So the natural base in ordinary Gromov-Witten theory is a stack of nodal curves. In log Gromov-Witten theory, a priori, without thinking too deeply, would be a stack of nodal curves together with a log structure. That's even more horribly infinite kind of than the stack of nodal curves, because now you can also add the log structure. But never mind, we never really seriously look at these stacks. And then there's this notion of an Artin fan in coming with any log scheme, and it's just given like gluing these kind of Artin stacks that I get as quotient of an affine toric variety by the maximal torus. So these are these stacks A sigma. And the way log schemes are built, these corresponding, if the sigmas are the tropicalizations so the dual cones of your sheaves M bar, of the stalks of M bar, then they come with natural arrows, and these translate into open embeddings, and you can take the co-limit of that to build a horribly looking algebraic stack, curly X, that we call the Artin fan. But then we notice that this is actually not so horrible, and it's kind of it's a tropical enrichment of the stack of well, it's a kind of a tropical, it kind of algebraizes tropical geometry in the following sense, that whenever you have a fs log scheme T, then the harms from T to this Artin fan are the same as a homomorphisms or maps. I shouldn't say homomorphisms. The morphism from the tropicalization of T to this cone complex sigma x. So this is a very tropical object. And then, as an application, we see that we can define a stack of basic stable log maps, not to our space X, but to this Artin fan. Okay, so that defines a certain Artin stack again, and this lives over this Artin stack of nodal curves together with a log structure. So of course this still goes on, right? So there's still this kind of, I don't know how to, I'm running out of M's here, but there's another M that would be the stack of nodal curves. So there's this factorization, and it turns out that already this thing here. So we had the perfect obstruction theory here, but it turns out also, well, first this map is actually very harmless, it's étale. In particular, this thing inherits also a perfect obstruction theory, okay? And that is the correct stack in log Gromov-Witten theory. And we saw this in action today because we can, when we fix the type of a tropical stable map, it gives you a closed substack M of x tau in M of x in the stack of basic stable log maps to this Artin fan. And of course, we can then kind of base change and obtain a virtual obstruction, a virtual fundamental class on these kind of strata, logarithmic strata, M of x tau in M of x. So actually, this is a slide I haven't done yet. So let me go a little more slowly. That was a slide I haven't done. So, okay, so we start with, we fix a type of this tropical stable map, and there's a notion of a marking by tau of a stable log map. So so what would that be? So whenever we have a stable map to X or curly X, I get a tropicalization. So maybe I could also write X or X. We get this tropicalization, which is a map of cone complexes, like this. And now a marking by tau means that I take one of the faces of QR dual and identify it with tau. So the tau would sit in here, okay, in such a way that this is part of the data. I choose this embedding, I choose and over tau there's this universal tropical curve over here, which is again a cone complex, and I choose an embedding here, okay? So that would be a marking. That means, remember the tropical geometry kind of is inclusion reversing. So if I choose one kind of type, I also get all the kind of generalizations of this that you have to include to turn it into, to get a space of marked curves to be closed. Yeah? I need all limits of these tau marked curves, which means I need to be able to generalize my tropical curve. So it will automatically contain all things that can degenerate to the tropical Tuya tau. Okay. So and then it's important to see that these strata are pure dimensional. Otherwise, I couldn't define a virtual fundamental class here. Be careful. This M of X, of course, may not be pure dimensional. There's various components and so on. But you can write down the dimension. And you see here this inclusion reversing, right? There's a minus dimension tau. B was a base, so if you work over just spec C, that's 0. But if you work over log point, then something comes in here. And if you work over the high dimensional base. Okay, so we get that this is virtually smooth, and that gives a refined virtual fundamental class. So this provides this enumerative meaning to any type of tropical stable map. And in Pirik's talk, you saw this when he said, I don't know what the notation was, but there was some little p, where he asked these curves to sit at a kind of the tropicalization at a point of the modelized space. Are there questions to the restriction of types?
Maybe I missed it. What's the relation between the type tau and the sigma c, the tropicalization of the curve?
Okay. The type is something discrete. So it just tells you where vertices go. I mean, like not where precisely, but in which cone a vertex goes, and in which cone an edge lies, and what the directions are. This is all fixed in families. This would be in a basic stable log map. That would be your tau down here. And then you have the universal family over it of curves. So that would be the sigma c. Yeah, the tau is always, I actually upuse notation, and I say tau is a type, and tau is also this QR dual, okay? That's kind of a convenient economy of notation. So I will always use tau for both denoting types and this kind of dual monoid down here that parameterizes. It's a tropical modelized space of curves of fixed type, of tropical curves of fixed type. Any other questions? Okay, so then let's move to the proper topic of today's talk. So I will eventually introduce the notion of punctured curves, but before doing that, I'll show you a good, already very useful application of this notion of marking by a type in these modelized spaces M of X tau. So let's look at some very explicit example. I look at the degeneration of cubics. Okay, a cubic famously has 27 lines, But that's not what we are trying to compute. We are trying to compute something more interesting, namely the number of degree 3 rational curves in there. These are always nodal cubics. And I'll show you how using a degeneration of your cubic, tropical geometry will give an interesting kind of decomposition of this count. OK, let's jump into it. So I'll start with this family that looks similar to the degenerating family of quartics, this degenerating family of K3 surface I had in maybe the first talk. So that's a family in A1 cos P3. It's a hypersurface. F3, I want a degree 3 general homogeneous polynomial, so the general fibers will be smooth. And the central fiber, or the total space, will have 9 A1 singularities. Okay, so just as in the quartic example. Then blowing up some irreducible components of the central fiber, as in the quartic example, I can resolve, do a small resolution, and obtain this normal crossings family X to X over A1. And the central fiber has these kind of 9 P1s, exceptional curves. Other than that, it's a union of 3 copies of P2, but they're a little blown up, okay, depending on which component are you on. And for T non-zero, of course, you get a toric surface, a cubic surface, which is isomorphic to the blow up of P2 in 6 points. Okay, so what is sigma x, the tropicalization of this geometry? It has one deepest point, one deepest logarithmic stratum. You might think of these and so on also have been, no, they are not the deepest strata. I'm just taking the central fiber. I'm not taking this boundary as part of our degeneration. And then only this is part of the divisor. Only this is the interesting point, and it's a codimension 2 normal crossings points. This just gives an R3 larger or equal 0. Which is a cone over the standard 2-dimensional simplex. Okay, so this is where we will do tropical geometry. So I can always do tropical, right? We really kind of do tropical geometry here, but then we can reduce dimension by taking the fiber over the point 1 in the tropicalization of the space, and that gives then this kind of polyhedral complex, and we rather do polyhedral geometry than geometry with cones. Okay, so the classical results that we are going to reproduce logarithmically is that there are 12 nodal cubics in a cubic surface through 2 general points. So I take 2 general points and look at where do I have nodal cubics. Of course, I have to kind of intersect with planes. They all like in planes, and then some of these contain a nodal cubic and some don't. And yeah, so let's see how we do this. So first we need to fix 2 points x1, x2 on the central fiber. I denoted them here, right? So this is my central fiber, just to take 2 general points. And you will see what general means in a second. Then there are 2 types of stable logarithmic maps. So type now used in a naive sense, not in the tropical sense, but tropical there will also be 2 types. So the one is as follows. It's slightly complicated to explain. You start from one of these P1s, okay? There's a unique line connecting this that intersects this exceptional curve and passes through this marked point x2, okay? So that hits that double curve in one point. Then there's a unique line connecting that point to the second mark point, and it hits somewhere here, and we don't want it to hit it in an exceptional curve. So there's one generality condition. Similarly here, right? We wiggle this a little bit. And then there's a unique line connecting that point to the exceptional curve again, and then you have to continue with the exceptional curve. Now, we normalize here. We don't connect the curve. Okay, just normalize this to get a rational curve. And then it's easy to see that this comes with a nice logarithmic structure. It's the image of a stable log map. If we tropicalize this picture, it's over a standard log point, right? If we tropicalize the picture, you see we have 4 vertices. These are the 4 irreducible components I have. I have two two marked points mapping to these two guys, right? So this is P1, P2. And then some edges that correspond to the nodes that you see here. So 3 edges. So that's the tropicalization. And this edge, of course, maps isomorphically to this edge and so on, and then have to take the cone over the whole thing. The contact orders at these points are 0, right? There is no log structure kind of in the vertical direction at these points. I can't put a contact order here really. I just take 0. The second type is maybe more interesting. Oh, so okay. So you look at this. You do your obstruction theory computation. That's very similar to ordinary Gromov-Witten theory, except you have to replace the tangent bundle by the log tangent bundle, which is kind of, it's a locally free sheaf. Okay. So and then if you do the computation, you see they're all unobstructed for rather trivial reasons, and you compute. So each of these curves computes 1. But there are 9 of those, right? Depending on which exceptional curve you start with. Well, if I start with some other exceptional curve, I have to be careful which direction I go and so on, but it works. Okay, so there are 9 such things, and the log Gromov-Witten count is 9. So now where are the remaining 3 curves? We wanted to get 12, right? So the second type looks very different. So another way to produce a logarithmic curve is as follows. You take this kind of tree with 4 of P1s with 4 irreducible components. You contract the middle component to this point and then add these 3 lines. So these 2 lines are obvious. They have a distinguished direction. Now what is really curious, and which would be a fun exercise in log geometry to figure out, is that the direction this line can go is fixed by log geometry. So to require a log stable map, a stable log map, so especially making this a log smooth curve or a standard log point, will fix the direction of this line. So it's not a one-dimensional moduli space, it's still 0-dimensional, okay? The tropical, so what's the tropicalization? Well, you have these 3 irreducible components. They are easy to see. They come here and here and here. And then there's one further component that maps to the deepest points. So this must map somewhere in the interior of this cone. But where? Well, you could now say, you could now do an analysis in terms of the contact orders that you have here for the edges, for these nodes. It's a little hard. Or you could use this kind of balancing, modified balancing condition that I mentioned and didn't write down, and that forces this point to be at the barycenter of that thing, and these directions will be -2, 1, 1, -2, 1, 1. Sorry, 2 minus, what did I say? 1, -2, -2, 1, and 1, 1, okay? So this is the only possibility. It will be at the barycenter. So what you observe, okay, so then I can say, now you have to do a little computation and argue a little bit to see that actually this guy contributes 3 to your log Gromov-Witten count. It's still unobstructed, but the 3 comes from some other lattice index. You can read it in the decomposition paper that we wrote with Dan Abramovich and Sheila Chen. Okay, what is remarkable and why I'm giving this at this point is that both of these tropical curves are rigid. So you see that we managed to split our Gromov-Witten count by looking at rigid tropical types. So rigid means it doesn't move. Yeah, you can't deform. So the corresponding tau is a one-dimensional array, meaning that if you intersect with your point 1 in the tropicalization of your base, you just get something tropically rigid. You can't move this. These points have to stay here. Yeah, you can't. Any movement would perturb. I mean, would give a different type. So. So what is interesting now is that the log Gromov-Witten theory of degenerations provide a natural refinement of the ordinary Gromov-Witten theory of the general fibers. And the summands that you get, like here, 9 plus 3, correspond to rigid tropical types. And that's a general statement. So that's the main result of this decomposition paper. You look at the moduli space. This really, we only have to do that statement. It has nothing to do with virtual, okay? We only do that statement for the moduli space of stable log maps to the Artin fan. There's no virtual thing. There's nothing obstructed and so on. It's the nicest work you can think of. And then you just push the button and say, oh, whatever I do here, it pulls back by standard intersection theory to your actual moduli stable log maps to X. So X0 is a central fiber, of course, right? The X comes also with the degeneration. It lives over A1. So this is central fiber. And beta is this corresponding whatever decoration that tells you that you fix the genus and the contact orders and so on. And you can write it as a sum over rigid types of the central fiber. And there are certain multiplicities that you can easily compute tropically. That's actually a very easy thing, right? So each tau of the rigid types maps to the base. And it's just which is in R larger or equal 0. And it's just the lattice index of that map. It's the index of that map. And then you have these strata. Okay? So this is what I said here. This is the lattice index of this map. And then you pull back to your actually stable log map. You have to be a little careful with your automorphism because the automorphisms of stable log maps here and stable log maps here to the Artin fan are slightly different. So, but if you do it carefully, you get this formula. And in the example, this is exactly this 12 equals 9 plus 3 that we get. Okay, so that's already a very useful application of log Gromov-Witten theory and of the notion of decoration of types. Are there questions? Okay, so this is still, if you look at this formula or that formula, that's still something, okay, you still have to compute really a moduli space and Gromov-Witten, log Gromov-Witten invariants on some complicated, possibly complicated space, okay? So if you have a degree 100 curve and you want to compute it, that's just a degree 100 curve, okay? Can't do anything else with it. The idea, of course, is, and that will be very important when we go to applications like Pierrick told you about, these kind of gluing formula, you want to actually use the fact that you can split your target, or better, your tropical curve, to find to write this kind of virtual fundamental class in terms of more primitive pieces. Yeah, so very easily, I mean, let's say in this example, if you look at this example, I mean, geometrically, you might think, hey, why can't we do some very simple computation where I do some computation on this component, some computation on this component, some computation on this component, and some computation very locally kind of at the origin. And that actually works, okay? And this is what the splitting does, which is a much harder thing. It took us a long time to get straight. And I mean, of course, in the end, once you understand it, it's very simple. But I'll show you where we had a problem getting it straight. Okay, so let me look at this kind of log smooth and proper family X over B. And B could be a point, a standard log point, or a curve with an origin. Okay, exactly the situation where you want to use degeneration results. And we want to compute this curly m or script m of x tau, the virtual fundamental class, by splitting tau along some edges. So in this particular example, what I mean by this is I have 3 edges that I can split. If I split the first edge, I end up in this thing. I get something that locally looks like this. You don't know what this arrow here means, but I'll give it a precise meaning very soon. And then you do some other things, right? At this point, you also get a mark point. Here also you get a mark point. And then you have one in the middle that has 3 arrows coming off. Okay. So we will interpret these tau i's that I wrote down here as tropicalizations of what I call punctured stable maps. And the punctured stable map is unlike the stable maps we had before, the stable log maps we had before, where the contact orders were all positive naturally. So if you remember these UPs, they all were, they had to do with legs that were kind of unbounded rays in some cone. So they are naturally elements, the direction vector is naturally an element in this cone. If you look at this thing here, right, this points inside the cone, right? It's parallel, it doesn't point out. So if you think of this kind of simplistic cone, it will hit this boundary at some point, so something is off here, okay? And what this actually means is that the contact order lies in sigma of P group rather than sigma of P, which is kind of a negative contact order. Yeah? So if you look at certain divisors and pullback functions to your curve, it will have a pole rather than a zero. It looks strange, right? But it can happen. And I'll tell you how to do this in log geometry very soon, but let's swallow this for the moment, and I'll show you what one of the main results is. The theorem A. So we split this tau at a bunch of edges and obtain some tau i's, just like in this kind of picture. So there's an obvious map, a splitting map, where I just split the curve at these nodes. So a node just produces, you normalize there, you produce two maps, and you just kind of restrict the log structure. You do a little bit more, but basically that's what's going on. So this is this map. And there's a similar map on the Artin fan side that would kind of gives this map. Unfortunately, this whole thing won't be a Cartesian diagram, and actually this map is very bad. This is where we kind of hit our heads against the wall for many years. The reason is that the gluing itself on the level of Artin fans is stacky in nature. In particular, this wouldn't be kind of a proper map or something. So you can't even do like push forward cycles and so on. It just doesn't work. Or pull back and so on, right? So instead, at some point, so we tried all kinds of things, and at some point after many years, Chile Chen suggested something. He suggested many things, and many didn't work, but this one did work. It was a fantastic idea. So he suggested to enrich these spaces with the evaluation data. So essentially, you do a fiber product that's over here. So for each gluing edge, so a gluing edge produces, a node produces two mark points, right, or two puncture points eventually. But let's first look at this thing. What is this? So at each node, you have an evaluation map at each node to this curly X. So if you have R nodes, you get an evaluation map to the Artin fan power R. And then of course there's a kind of classifying map so from your X to the Artin fan, X to R to curly X to R, which is strict, so logarithmically boring in a way. Yeah? So all the log structure of X comes from this Artin fan. And it's actually smooth because we assumed X is log smooth. So this is a smooth map, and you do this fiber product. And that gets rid of the stacky nature of the gluing. Once you do that, this map, so you do a similar thing here, right? Yeah? Except at the nodes, now you do it at whichever split mark points you got. So this gives some diagonal map here that I call delta Eve. And this now becomes finite and representable. Representable means non-stacky, okay? So this is wonderful to do intersection theory, right? A finite representable map, who cares, right? You can push forward, pull back, and so on. So this is wonderful. And the whole diagram, this diagram here, is Cartesian, and it's compatible with virtual fundamental classes. So again, this kind of perfect obstruction theory lifts to that place, and it pulls back to a VFC here that's compatible with this whole picture. Everything works. Okay? So in principle, that achieves the kind of gluing formalism. The questions here? Okay. So just re-emphasize here, right? So working with this evaluation stack gets rid of the stacky nature of gluing stable punctured maps in these M of x tau I. And this map is smooth, hence this map is also smooth. So these are kind of harmless, these arrows here. But they are stacky, of course. So this means, what does this mean? So if you now are interested in computing something over here, so computing the virtual fundamental class here, you can do this by pushing forward, right, and computing here. But it's compatible with the virtual fundamental class, so that means all we need to know is what's the image of the fundamental class here in this space, okay? So that has a fundamental class, finite pure dimensional, if you do the tau correctly, and it has, yeah, it is pure dimensional, and you can push it forward, it gives some class here, and then you'd virtually pull back, and that gives the same computation as here. So this is how gluing works. And so theorem A reduces the computation of this thing to computing the push forward of that fundamental class. One interesting feature of this is, you see, this only depends on the ordinate fan. Actually, I lied. I wanted to change this and somehow forgot. It depends. This is not quite right what I wrote. It does depend on x, but very mildly. It only depends. So it certainly depends on sigma and on tau. That's discrete data. That's very insensitive to the geometry. And it does depend on the gluing strata. So no finer information. Whatever happens is happening in X away from the gluing strata has nothing to do with this kind of problem, okay, computing that thing. So how does one compute that? So there's a second important diagram. It looks a little funky here. Ignore the tilde and prime for the moment, okay? So basically it says, how would I compute that from the corresponding individual pieces? So how do I compute delta eve of the fundamental class of that guy? There's another Cartesian diagram that tells you, well, it's kind of obvious, right? So this is a proper gluing diagram. Before this was kind of a splitting diagram. I just split this curve in these individual pieces, but now how do we glue? Gluing has something to do with doing something on X. This is what this diagram does. So we have the diagonal map from X, one copy of X for each splitting node, and it goes to the kind of 2 points you want to glue. And there is an FS, ignore this for the moment, Cartesian diagram like this, okay? What's doing the tilde and prime? That's a slightly technical point. The tilde means, to make this actually a Cartesian diagram, I have to enlarge the log structure. Simply, this is happening at the gluing nodes, not at the moduli space. So rather than the basic monoids, what you have to do is you need to look at the log structures that happen at the nodes. So there's an additional n squared factor in there. So this does the m tilde. It doesn't change your underlying problem. The underlying stacks are the same, okay? The prime is maybe a little more annoying. The prime is you need a slightly weaker notion of marking it. I haven't given you the really technical definition of marking. Actually, the definition I gave you is a weak definition that goes in here. Anyway, you have to change the definition of marking slightly, but that only changes the non-reduced structure of the stack, which doesn't matter if you're interested in pushing forward fundamental classes. Okay, slightly technical point, don't pay attention to it. So the point is, this diagram is good enough to compute. If I know how to compute the push forward of the fundamental class here, I'm good, okay? If I know how to handle this diagram. So, but it's FS Cartesian, it's not just Cartesian. So what is this? FS Cartesian, I already mentioned this in my first talk. Fiber products in log geometry are very sensitive to the category you work in. FS Cartesian is the right notion when you work with FS log schemes. It is modeled on the fiber product of cones. That seems obvious, right? So what I want is the following. If I have two cones and two maps to a third cone, I can take the fiber product. Just a set theoretic fiber product is obviously a cone. Okay, so if these two maps are injections, it's just the intersection of sigma 1 and sigma 2. And then I would like to have that the fiber product of the corresponding toric varieties, this thing, is a fiber product, is the toric variety of the fiber product. And that's wrong. Okay, that's wrong in general. And the FS fiber product makes us correct that statement. Let me look at one example. Let's look at tau to be the quadrant, R2 larger or equal 0. And sigma 1 and sigma 2 are two rays, which, however, are not the same, so they only intersect at the origin. Then what turns out is that the intersection of these things, of course, the fiber product is just the origin. What does this mean now geometrically in terms of log geometry? So let's look at A2 with this toric log structure. And let's take two lines, A1, A2, also with a toric log structure, not with the one induced from the embedding. Okay, so at this, for C1, I have an n here, not an n squared. Similarly for C2. Okay, I want the R larger or equal 0. So I said Ci is an A1, 0, so it's not these maps are not strict. And then, sorry, I missed the most important thing here. The Fs fiber product of these two curves in A2 is empty. Okay? How does one understand this? You could kind of blow up this point and take the strict transforms, and then you see they are disjoint. And the Fs fiber product is compatible with these kind of base changes. Okay, so it is a good fiber product for these things. Of course, it makes computing that thing here slightly more tricky. Are there questions to this Fs fiber product?
Sorry, just maybe before. So what's the relation between the theorem A and B? Is the B that explains A or?
No, they're kind of separate things that you both need to do gluing. So theorem A tells you how the script M corresponds to the frac M. Okay? So that reduces computing this gluing thing in computing the push forward of the fundamental class of frac M Eve. Okay? Theorem B tells you, has nothing to do with the script M's, okay? That's only working on the level of the frac M's. And it reduces the computation of this push forward to this, I mean, it kind of explains how this is related to gluing curves in X. Yeah, so this brings in these kind of factors of X.
So there's the innovation of evaluation stack. I mean, can I see clearly why it works in theorem A? You said it's a key point to.
Theorem A, in a way, yeah, how does one see this? I guess it would lead us too far afield. Okay, maybe we can discuss afterwards where this is coming in. Okay. Okay, so still this may still be sometimes difficult to compute in practice, but there are some very good cases that are very useful. So my student Yishan Wu, in her thesis, did the following thing. So assume that the gluing strata are isomorphic to toric varieties with their toric log structure. And that happens quite often, right? So if you think like you want to, or not, I'm not sure what is often, but there are many important cases where this happens. For example, your gluing strata are just points. Yeah, so these are kinds of the tropical generic things. That's what's happening in Pierik's kind of setup. Of course they are toric, right? A point is toric. Or you have a one-dimensional thing that happens to be rational and has only two special points, and it's a P1, and it's also toric, okay? And these are the two cases that are probably most important. Or there's some toric geometry around. So then you can compute that thing, and that is, her thesis was entirely built on analyzing this diagram in theorem B, okay? So you analyze this diagram, then you can compute this tropically, as a sum of products of strata in these evaluation stacks, frac M stacks. So the formula looks as follows. So this is a push forward we want to compute. When you take a sum over certain types, these are, of course, generalizations of the types tau I we had here, okay? So they are deeper strata of in here. And then there's a tropically computable multiplicity. And it's a sum over that such thing, and then you take the product of these strata corresponding to these generalized types omega I for each I. Okay, so that's computable. And the sum is over solutions of a perturbed matching problem for the tau I. So if you think of your tropical of tau, you cut certain edges, and then you introduce certain displacement vectors and ask, can you still match? That's what will give you the omegas. I'll do an explicit example, okay? So the sum is over solutions omega I of a perturbed matching problem for the tau I via chosen displacement vector for the gluing edges. So let's do a very simple example. I look at the degeneration of P1 cross P1 to a union of two copies of P2. So that is just the total space will be a toric variety corresponding to the fan given by the cone over that thing. So put that diagram in height 1 and take the cone over it. Okay, so it has 4 maximal cones, this fan, and with a little experience, you see that this actually the general fiber is a P1 cross P1 that has to do with the recession cone that you see in this picture, or the recession fan. And it has 2 copies of P2 that has to do with the 2 vertices that you see here. And you see the fans of P2 coming up. In any case, there is such a toric degeneration where x0 looks like this. So 2 copies of P2 glued along one coordinate line. And I look at curves of by degree 1, 1. And I can certainly write down degenerations of such curves to diagrams like this. So these are 2 lines, one on HP2, and they match at the double line. The corresponding type tau for this thing is just essentially the one skeleton of this B that I wrote down here. So it's just this curve that sits on top of the one skeleton of this B. Okay, so that's my type tau that I want to compute. Now, I split. There's only one edge I can split, right? So here I split. And I choose a general displacement vector. So that's a vector in here. The torus action tells you that this makes sense. So the torus action tells you there's some kind of vector that you can shift to both directions. It lives in each cone. And then you look at the displaced matching problem. So you want to look at types of tropical curves, omega 1, omega 2, that match up to this displacement by psi at the splitting edge. Okay, so this gives these 2 types, gives this type, and the other one that has the correct dimension looks like this. So there are only 2 types that you can do. And that would be the kind of matching that you see here, right? So you get 2 summons, one corresponding to the omega 1 and omega 2 here, the other one to the omega 1, omega 2 here. In geometry, it means you would act by a torus action corresponding to a GM action corresponding to this vector psi and push this line into one of, what is it? You push it into this vertex, into this divisor. Or here you push that thing in that divisor, okay? This is what this is doing. So the proof is this psi, this tangent vector, defines a GM action on these moduli spaces. And that you can use to define a rational equivalence between your cycle and a product of strata. Okay? A sum of products of strata. And that's what this is. Okay. Other questions on this kind of gluing formula? Okay, so then I promised, so in the splitting formula, we already had punctured curves, but I didn't explain what it is. So let's do that now. So a punctured curve is almost as before, but before we had at the mark point, we had these Q direct sum n monoids. Yeah, and now we allow submonads, bigger submonads of Q direct sum, Q group direct sum Z, namely containing Q direct sum Z, and there are two conditions. First, it should at least contain Q direct sum N. That's the stuff coming from the marked points. And whatever you edit, so whenever this K thing in here is less than 0, you want the alpha morphism. That was the thing. What was alpha? Alpha was the morphism from MC to OC, okay? That thing, or rather the alpha bar maybe. So this goes from that should be, sorry, alpha of Q. That's a slightly bad notation. Let me leave it like this, okay? Alpha of Qk is 0 whenever k is 0. So that means whatever you added to your log structure should map to 0. So a very simple example is if you start from a kind of mark point over log, standard log point, rather than taking this kind of monoid, you take something slightly bigger, okay? You shouldn't, but however, you shouldn't get the illusion that it's always as simple, right? It's not just one ray that you add. So I've tried to draw a diagram here that took me a long time to get here. It's probably still not good. When the rank of Q is larger than 1. So the Q, this is your Q on the base, right? So you do have a projection to Q. The Q sits in this Q direct sum that up here, of course, is the Q direct sum Z, or Q group, QR direct sum, QR group direct sum R. So this Q sits inside here at height 0. And then we have everything above, right? That is this kind of big thing here. But then you can have anything below that is kind of rational polyhedral. So some cone generated by some stuff coming off. So I've tried to draw some cross section here, and that would look like this in this example. Okay, so this is what can happen in these punctures in general. So punctures appear naturally when you split nodes. So this is what we did in the gluing formalism. So you start with a stable log, with a log curve, log smooth curve. You have a node Q, and you just take one irreducible component, some component that intersects this node only in one branch. Okay, and then you take the punctured log structure on C1 to be just the induced log structure that you get from C. And that has a puncture at this point. Why is that? So the M bar at this node, as we know, had this form Q direct sum n squared. So this was the 1 mapped to the diagonal, 1, 1 on one side, and here it got some element rho in Q. So it looks like this. And then it's isomorphic. We saw this, I computed this explicitly, gave you the equations once. It's isomorphic to the submonad of Q direct sum Z, Q group direct sum Z, that is generated by Q direct sum n and one more element, namely rho minus 1. Okay, so in this case, the cross section is really just 1 point. So it's generated by these three parts. So Q, of course, right? Q direct sum 0, then 1, 0. Sorry, 0, 1, of course. That's 0, 1. And rho minus 1. Okay, so this appears naturally. That's how our punctures appear. So, and then you can upgrade your theory of stable log maps to stable punctured maps on a naive level that goes very easily, but the details are sufficiently complicated at some point, but it all works. So you just look at your upgrade, your diagrams admitting domains to be punctured curves. And there's one important stability condition that we have, an additional stability condition, kind of a logarithmic stability condition. Namely, we want that the puncturing points at any of the marked points possibly punctured or still marked. The log structure is generated by Q direct sum n, of course. And then just everything coming from x at this point. Okay, so you pull back your m bar x f of p by this f, and and take that. So in other words, we take the puncturing as small as possible. Let's see, the smallest puncturing you can write down such that such a map still exists. There's a price you pay for this kind of canonical definition. Namely, I told you there's one place in all my talks where non-saturated log structures appear. It's right here, right? Because you pull back some log structure, some monoid by some map, that may not be saturated, right? And the reason is, if you might think, oh, why not saturating it? It screws up all your base changes, okay? It's awful. Don't do it. So this is a place where you don't want to saturate, but trust me, it's a non-issue, okay? Just don't touch it. You don't want to compute it. It works marvelously. Everything is as you expect. Don't saturate. Okay, so then tropical interpretation now. So what does this mean tropically? So if this m bar at a point is not, as a marked point, is not Q direct sum n, but has some honest puncturing, that means that the legs that you write down, it's an exercise in dualizing cones, is bounded. Okay, so we are dual, right? So your monoid becomes bigger, the dual monoid it becomes smaller. And then this condition translates into that it is still as large as possible, right? So this is as small as possible. This means that the leg is as long as possible. What is the maximal length? It hits the boundary. Okay, so in these pictures we had before, where was it? Here, right? So this wouldn't be the picture we get. What we really get is a puncturing, a tropical curve that extends all the way. It doesn't work. Okay, all the way to the boundary, like this. Okay, so that's actually what we do, and similarly for the other diagrams. Okay. So with these modified or generalized definitions, we get the notion of tropical punctured maps. Now you have these bounded legs, possibly you have types of tropical punctured maps. The definition of basicness is unchanged, formally unchanged. You still have moduli of now tropical punctured maps, and the basic one is just a dual of that. So and that thing becomes, and then this thing becomes is still virtually smooth, so no problem. There's a subtle point, maybe I shouldn't have mentioned it, but I don't know, I couldn't resist because we spent so much time getting confused about it. So if you do this naively, you see that the m of x tau, I have 5 minutes, right? We started 40, or even a little more. Okay, good. It's actually my last slide, so I might even finish. So m of x tau, if you do it naively, the way I've presented it at this point, may actually not be log smooth over the complex numbers. So it, i.e., may not have, right? May not have toroidal singularities. Yeah, log smooth over this trivial log point meant toroidal. Okay, so has toric models up to some smooth cover, right? We are in stacks. Rather, it is locally isomorphic to the real zero locus of a monomial ideal in a toric variety. So you have a toric variety that looks like, why did I do a dual here? That's too much. C of PZ, and we look at the monomial ideal. The zero locus is, of course, a union of strata of closures of torus orbits of various dimensions, plus it can have non-reduced structure. So it's slightly horrible. So in particular, it may not be pure dimensional. But a key insight was it is still pure dimensional, so can be used to define log Gromov-Witten invariants if your tropical punctured map tau is realizable. And realizable just means your punctures shouldn't point out of a cone. So what I mean is, if you have a cone here and the puncturing, so you have some curve, what do I know, right? And then there could be a puncturing that kind of points out. That's not allowed. You don't want this. That would not be realizable, okay? So it has to move a little away. So, but the tropicalization of any honest punctured stable map is realizable. That's where the name comes from. So these are the ones you are really interested in. So, and restricting to realizable ones, you do get pure dimensional spaces. Sorry, where is it? This M of x, curly x tau is pure dimensional. So that means for these punctured stable log maps, you do get Gromov-Witten invariants, punctured Gromov-Witten invariants. Yep.
Theorem A and theorem B also for this new setting?
They do involve the new setting. I kind of swept it undercarded. So because we split, right? So
the tilde prime, so tilde prime is related?
No. Okay. Yeah, maybe I confused you a little bit. So if you look at this map here, or this map, you split nodes. Each splitting of a node introduces puncturings. So these moduli spaces are punctured moduli spaces. These aren't, right? That's or may not be. They could. It also works for puncturings, but even if these are not punctured moduli spaces, these ones are. I mean, moduli space of punctured maps. And then the tilde, yeah, you see, this has nothing to do with puncturing. There's still a tilde and a prime.
And that right hand side then?
Again, these would be the punctured ones because this is the lower line of that one, right? So I could have drawn a big diagram to make it even more confusing and put it in one theorem. But yeah, so this lower line is the upper line of theorem B, upper row. Okay? So let's finish with one example, how this comes up. Let's look at the blowing up in one point, non-toric blowing up of P1 cross P1. So this is this kind of picture here. You have an exceptional curve. And I look at lines like this. I missed to put, whoops, what am I doing? I missed to put in 2 marked points. So this is the general element that you have, this one. The tropicalization would just be this kind of curve. Yeah? So you have two marked points with contact orders 0, 1, 0, -1. Now there are 2 degenerations. One is a harmless degeneration over here, so that's similar to what Pierik had in his talk, right? So it meant that this thing generalizes to this kind of curve, tropical curve. Yeah? Or conversely, this curve degenerates to that one. The more interesting degeneration is when you take CT to that side. So this, then you get a union of that with the exceptional curve. If you did that, you would just get this kind of tropical curve. So the diagram is slightly confusing. Let me see. This is normal crossings, right? So we have 4 copies of a quadrant. You see them here. Here are 3. And the 4th one, the one here, I've written slightly differently, but it's still isomorphic to a quadrant. Yeah, so there's this SL2Z transformation that turns into an honest quadrant. Why have I written it like this? Because that's the correct affine structure that shows you the balancing condition. Okay, so you have to identify these two sides in a cone complex. So if I did that, that's still the image of a stable log map. If I tropicalize it, it has 2 irreducible components. One mapping to the interior of that thing, the other one to the boundary, so that would be this kind of tropical curve. And it's balanced up to this point. Now we punctured the thing by removing we can puncture it by removing that exceptional curve, splitting this edge, and leaving us with this kind of arrow for the puncturing. Okay, so this is one way you actually honestly see a punctured curve. Interestingly, this point here is free to move. So once in the degeneration, of course, the puncturing appears here. Actually, I'm somewhat slightly confused by this. I think it can move, okay? Anyway, so here's a punctured curve, and you also see that once you have, maybe that's a good thing. Once you have a puncturing, obviously, because the contact overlap is negative, the irreducible component containing the puncturing has to map into the divisor. Yeah, it's not possible to have this, the image of this kind of thing kind of going like this, right? Because then you would have a positive contact order here. But still, not the whole curve has to lie in there. I mean, there could be other components coming out and then forcing this one component in there. Okay, and tomorrow I will show you a striking application, what I find a striking application of all this kind of theory to produce intrinsic mirrors. So mirror symmetry is the way it should be done, okay? Without any ad hoc construction, completely canonically, starting with something that birational geometers would give us. Okay, I'll show you to do this. These canonical wall structures that Pierrick mentioned will come up.